Brown in 1975. Came here in 1978. One of two people hired by the former department head, James Ortega, special prize to anybody who can name the other one.
It's three. Twice? 10?
No.
Martin
All right,
Bernstein.
no prizes will be awarded. He became a fellow of the Institute of Mathematical Physics in 2007 for seminal contributions to the theory and applications of random matrices. He and Zhidong Bai are the authors of Spectral Analysis of Large Dimensional Random Matrices, first published in 2006 in China, quickly sold out according to Review and Math Reviews. Second editions by Springer in 2010, and the reviewer says it's going to be a classic in the field of random matrix theory.
Would you hear that?
Plus, in addition, among his other awards, there, if you go to the Flying Saucer bar downtown, there's this plate with his name on the roof, on the ceiling.
200 years. Okay, this is a probability talk. I will use some terminology. Figure out things. What I want to begin with an introduction, a background of what types of matrices I look at. And they are coming from basically estimating a covariance matrix from a random vector. So if we have a random vector that's little n dimensional, so think of it as a column vector, the components, we'll assume that they mean zero, finite variance or second moment, and they can be complex. And the covariance, no mean zero, will just be the, for any ith element, any two components, will just be the expected value of one times the conjugate of the other. And the population covariance matrix is always defined to be the matrix consisting of all those covariances. Sometimes you say covariance, variance, covariance matrix. And it's really just, you take the outer product. That's, there should be a asterisk there, which means conjugate, Hermitian transpose. So it's an outer product. This is a column times a row, you get an outer product, you get a matrix, and it's the expected value of all the individual components. So let's say you have capital N independent copies of this thing. And as an estimate, that's used in classic multivariate statistics, folks, for years. You take the average of the outer products of all those samples. Okay, and here, which you should know that this is you take the average of them. You have capital N of them, and this is you can express this if you have the matrix Y is just matrix full of the columns of the sample vectors. That's just a matrix times its transpose. Law of large numbers, for fixed dimension little n, you'll let big N go to infinity. You will have this thing converging to the population covariance matrix as the dimension blows up. Okay, that's the fixed dimension. But the work I do involves letting the dimension blow up along with the sample. In the case where X is multivariate Gaussian, real or complex, then you can always express S as the random vector X as a matrix or any non-negative square root of the population matrix times a vector Y which consists of independent components, where in the real case they are standardized Gaussian. In the complex case, they are the real imaginary parts are independent and both normally distributed with variance 1/2, not 1 in the complex case. So this is traditionally known, that the sample matrix is traditionally known as a Wishart matrix, the sample covariance matrix, when it is X is multivariate Gaussian. In this case, the matrix Bn can be expressed in this form, where you have the independent elements. The X consists of IID standardized Gaussian entries, either real or complex. The matrices I look at are of this form, except, well, for various, or at least the first result I'll present, these can be random, this matrix itself, but the X's are full of independent, identically distributed random variables, not just Gaussian. And that's the extension from multivariate statistical analysis involving Wishart matrices. And I'll be looking mainly at eigenvalues and specifically what we call the empirical distribution function of the eigenvalues of a matrix A, let's say it's P by P, and if it has real eigenvalues, this gives you, it's really the probability measure induced by the P eigenvalues putting equal mass on the eigenvalues. So for the distribution function, for any x, you count the number of eigenvalues less than or equal to x and divide by the number of them. The proportion of eigenvalues less than or equal to x. And for any probability distribution function g, the Stilter's transform is defined by this integral. Here I take Stilter's integrals here. This is called Hilbert transform, Cauchy transform, but traditionally we call it Stilter's transform. My original paper back in '67, Marchenko and Pasteur were one of the first to work on these matrices. There's a famous inversion formula. This is why this is very useful. You have an inversion formula. One can easily work this out. This is the imaginary part. The imaginary part of this thing. Yeah, Z is complex. In the complex plane, the imaginary part is positive. And this, you can easily work it out when A and B are continuity points in the distribution G. And main reason why it's very useful for eigenvalue behavior is because the Stilter's transform of the empirical distribution function of the eigenvalues of a matrix A is simply the normalized trace of the resolvent of the matrix. And that comes up very often in proving things. So this main result here is a culmination of other works, really starting from 1967, but the one that I worked on includes this limiting formula specifically, and also generalizes just the second moment. And let me just jump down to here. So I'm going to define this matrix Bn by this, which is like in the Wishart case. The Xn is defined here for any little n and big N. Xn is little n by big N, complex, can be real imaginary parts, can be anything, identically distributed for all n, I, and j, and for every fixed little n, they are independent. So you have little n by big N matrix, and they're all independent of each other, same distribution. You increase little n and big N, you'll have another set without any relationship between the dependencies of the elements of the random matrices as you increase little n. We assume that big N is a function of little n, where the ratio goes to a positive constant c. I call little cn, that will appear later, as little n goes to infinity. So I'm looking at situations where the vector dimension and the sample size are both increasing, but in the same order of magnitude, going to a positive constant c. Not zero, not infinity. Tn is assuming, and for this result, in my paper, it could be random, Hermitian, non-negative, definite, with the empirical distribution of the eigenvalues of Tn converging almost surely to a distribution, a proper probability distribution function, H, on the non-negative reals as n goes to infinity. We assume that Xn and Tn are independent. Denote this by the Hermitian non-negative square root. It could be any non-negative square root. In fact, once we get a result on non-negative square roots, this matrix here, when we pre and post multiply, can be any rectangular matrix that you want. It's just that the population matrix will be that matrix times its transpose. But for convenience sake, we can take it to be a non-negative square root, the non-negative square root of Tn. Now this, I say obviously, everybody in matrix theory knows that A, B, n by n, the eigenvalues of A, B, the eigenvalues of B, A are the same characteristic polynomial. So if I put the square root of Tn, which is square, on the other side, the eigenvalues of this matrix are exactly the same as the eigenvalues of the original matrix. And the result is almost surely the empirical distribution, the eigenvalues of Bn, converges in distribution as n goes to infinity with probability 1 to a proper probability distribution function whose Stieltjes transform satisfies this equation. So for any z and the positive reals, the positive complex plane, m will satisfy this equation. Okay, in the sense that it's unique for the set of all m's for which this is true. Now, this is an equation. Actually, I use this to prove the theorem. But something that I realized back in the late 80s was that if we bring half of this onto the other side, we'll get x star tx. Okay, the eigenvalues of x star tx are related. Right? When the matrices are rectangular, if A, B, and B, A, so this is little n by big N and n by little n. If we reverse the two, then the eigenvalues are the same, modulo some zero eigenvalues, depending upon whether little n is bigger than or less than big N. Because of that, we have the empirical distribution, the eigenvalues of x star tx, to be related to the empirical distribution, the eigenvalues of this guy here, or square root of t, x star square root of t, through this equation. This is the indicator function on the non-negative reals. I left out the x. It should be an x. But for these three functions, it's fairly straightforward to see this. And so the empirical distribution, the eigenvalues of x star tx, will go to this. It's little n over big N goes to c. And we'll get this. And I'll call that F underline. Well, it turns out, this is algebra. I only put in one step. But if you replace the m by m star, you're going to get this relationship here. And with just some basic algebra, move that z into the numerator and add and subtract, add mf underline t, and add. We're going to get this equation. What this gives us is an explicit expression for the inverse of the limiting empirical distribution function of the eigenvalues of this matrix, which are related directly to the eigenvalues of our sample covariance matrix. Okay? And this was something that I exploited to the hilt to try to, I want to understand how the limiting distribution behaves. Okay? It satisfied that previous equation was not very useful. This is very useful. We have an explicit expression for the inverse of the limiting distribution of the eigenvalues of the matrix where you move it halfway. Properties. This was something I worked out with my student in the early 90s, Sang-Yul Choi. The first fact is that endpoints of the connected components of the support of F are given by the extreme of these things. Of this function. This is the same function given earlier. This comes from the fact that, so if you have for any distribution function, g, when z is on the real line and outside the support of the distribution, so when z goes onto the real line outside the support, this is well defined. And its derivative, you take its derivative, you're going to get 1 over lambda minus z squared. The derivative is positive. So on the real line, z outside the support of your distribution, its derivative is positive, which means that outside the support, this function is increasing. It's an increasing function. Okay? And so if you plot this function outside, you're going to see places on the real line where this thing is increasing. This function here is the inverse of this function. This is m of z, and when g is a limiting distribution, this guy here is the inverse of it. Well, a function that's increasing is its inverse exists and is also increasing. So the idea is that if you plot this function, when m is outside, when m minus 1 over m is outside the support of h, this will be well defined. Plot this function wherever this is well defined. You don't want to make this blow up. So keep m underline away, that would make this here, that is minus 1 over m, is going to be away from the support of h. H, again, is the limiting distribution, the eigenvalues of the population covariance matrix. Plot this thing on the real line. Places where the function is increasing, if you look on the vertical axis, that will give you places outside of the support of the distribution. And this was something, this was originally mentioned in a paper by Marchenko and Pasteur. They did not look at this result at all. But my student and I, we worked together if and only if. On any place where this thing, any and all places where on the vertical axis the function is increasing, this will be outside the limiting support. We also proved that this guy here is a continuous density away from the origin given by this function. This is the imaginary part of the m underline, you divide by c times pi. And so for positive x's, we know that the eigenvalue is always going to be non-negative. X is in the support of f, the imaginary part. Where this is the limit also that we've shown, you take the limit as z on the complex plane goes onto the real line onto any particular x. That's what we mean by this. And this is something we did prove also. As z goes onto the real line, this thing exists. And also, we also show the imaginary part will give us our density. And this thing, this guy here solves, and also what we proved that on the real line it will also solve that inverse function. Some other properties. F, the actual, the function f, that's an f prime there, right? So the derivative is actually analytic outside its support. And in more than cases where the limiting distribution is discrete, places where the support hits the real line, it goes down like a square root function. It goes steep like a square root function. We actually showed that the behavior divided by the square root of the function minus whatever that value is there. Let's say that's an A0. That the ratio of the density goes like that. This will go down to 0 at that point. This will go to a constant. It's more than what I just said here, as far as infinite slopes. The fact that you knew C in capital F, then you could go back to determination, at least theoretically. This is the crux of my talk. I thought that this was just something that you can at least examine theoretically, but not be very useful for real situations when you have real data. This should make sense that the limiting distribution function f goes to h and c goes to 0. C being very, very small means a lot more samples than vector dimension. So the law of large numbers may kick in. Intuitively, if you have a lot more samples in vector dimension, then it should, and it does, and it is true that as c goes to 0, that limiting distribution does go to the distribution of the population eigenvalues. What I'm going to show you next is one simulation with one example that I've had on my website for many years. Situation where the population matrix H involves 3 distinct eigenvalues, 1, 3, and 10, with proportions 0.2, 0.4, and 0.4. And I did lots of simulations with various C's. I think C and what I'm going to show you is 1/10. And little n is 200. Okay, in this case, what you're going to have for the inverse function, it's minus 1 over m, hat plus whatever the C is, times, what are you going to have? You're going to have 0.2 times 1 over 1 plus 1 times t, plus 0.4 times, m, t is 1 there, m underline. And you'll have 4 times 3 over 1 plus 3m underline, plus 0.4, 10 over 1 plus 10m. The next one here. The one on the bottom is actually a plot of this function for m real. Okay, notice we'll have we get vertical asymptotes at minus a tenth and minus a third and minus 1. And C in this case, I'm pretty sure it's 1/10. I remember on the next transparency. And this is using Newton's method, finding the imaginary part, knowing where the bound. Oh, let me mention this. So places where it's increasing, where the function is increasing, we're outside the support. Here it's coming from minus a tenth and coming. It actually can show it's convex between the largest negative reciprocal going upward. And so we're outside the support here. We're outside the support here. This is increasing outside the support, and coming up, we're also outside the support there. What's left is the support of our distribution. And so this region here corresponds to this one, and here corresponds to this. And I get these values by doing Newton's method. For a specific x here, I figure out the m, what matches it, and I uptick it, what the program costs. This, the next one, this is an overlay from one simulation where little n is 200, yeah, C is 0.1. And this kind of shows you that this is a histogram of the eigenvalues from one simulation. The density should match the histogram. Okay, or the histogram should be close to the density. So, and it looks pretty well. I did it very crudely. I went from smallest to largest, and I divided up into so many. I forget how many it was. 30, I forget. And just counted the bins and divided so that the total mass is 1. So match up. Everything I told you so far just talks about limiting distribution of the eigenvalues. That gives you proportions. It tells you proportionally there should be so many in certain intervals. And and actually one could show the limiting distribution. It should make sense that you go proportionally. This is 0.4. The mass of this is 0.4. The area of the curve is 0.4, 0.4, and 0.2. But nothing telling you about properties of individual eigenvalues. Where you can get an idea that something more is happening, more than just what my that first theorem said. This is a scatter plot of those 200 eigenvalues. And trust me, there are 80 here from 200 dimension. 80 here, 80 here, and 40 there. And notice there are none outside. Okay? And I should mention, this is the theorem that I mentioned, you do not have to assume that the means is 0. Basically, if you have, you go from a matrix that has non-mean 0, you subtract away the means, you're subtracting a rank 1 matrix. There should be overlays. The interlacing property of eigenvalues should tell you that you're not going to have any difference in the empirical distribution. But here, the simulation was definitely would mean 0. Notice practically none is made a little overshoot there. Something more is going on as far as how these random matrices are behaving. In the case with dimension 200, it's actually happening lower also. But I mean, most of our results are in terms of letting the dimensions blow up. So relevant information is telling you for n large, things are behaving. This is something I was interested in the late 80s. How many remember Stephen Wright? How many remember Stephen Wright? He came back from Stanford, told me about the work that the engineers were doing, the STI business, the Star Wars. You got enemy things out, what they call it, things out there emitting signals onto a bank of antennas, and you want to know how many are out there and where they are. Okay, so you can shoot them down, whatever. And the first step, you're sampling from the antennas, and you form a sample matrix that approximates the population one. The population matrix, it's going through noise. You basically have the population matrix, you will have one small eigenvalue alone with a certain multiplicity. And the multiplicity minus the number of antennas will tell you how, the other way around. The number of antennas minus the multiplicity will tell you how many enemy things are out there. That smallest eigenvalue they call the noise eigenvalue. And this is going through ambient noise. And Stephen and I, we worked together on this, but fixed dimension, fixed enemy things out there. But I was wondering, what if there are, a lot of them out there, 100? This is actually a demonstration of the curse of high dimensionality. Just in the case where you sample 10 times the number of your dimension, you don't do so well getting an estimate of 10 here. It's scattered about it. So this is an example of the curse of high dimensionality. And none of the engineers were even considering, what happens when you vector dimension. The number of antennas is sizable. They always assume you have enough samples, The curse of high dimensionality is telling you that you're going to need a lot of samples, which is sometimes, not feasible. Right? World War III will occur.
So let me understand what you're doing. So I'm not in this field. So basically what you're saying is like, for this particular experiment, you have a matrix with 3 eigenvalues, right?
The population matrix, yeah.
One, and then you generate those Tn and Xn, which are random, and Xn are uncorrelated. How did you generate that again, like, essentially? And then this is just you're showing the distribution.
Actually, I assume that actually they were Gaussian.
Gaussian. So, but this is just the population distribution, how you
this is from a result of a sample. It's the matrix Bn. Okay, so Bn, T1 half, XX star, T1 half.
Yeah.
So this was a matrix, I assumed it to be diagonal. So many 1, so many 3, so many 10. Well, square root 3, square root of 10. And this was a matrix full of independent identically distributed
So you put a Gaussian.
Yeah. And this is one simulation.
Okay. So one simulation, and then you generate the distribution of the eigenvalues that are coming out.
No, these are the eigenvalues. I did one simulation, I have 200 eigenvalues, I plotted them.
Oh.
Okay, and here is from the 200 eigenvalues, this is a histogram of them. And here I overlay what the limiting density should look like. Okay, so the stuff with the Star Wars business, I put in a proposal, NSF, to work on, when the dimension blows up, gets larger and larger, things get lousy, and but at least when I propose it, I'd say at least we have an idea of the proportion of the noise eigenvalues. Here, let's say this is what corresponds to the noise one. Traditional, and this is what all the engineers were looking at. You want to get some estimate of the smallest eigenvalue. They wanted enough samples so that all the eigenvalues will be near each other, close to each other. But I propose, well, no, don't just get enough samples so they separate. They separate, and at the very least, you'll get the proportion of eigenvalues working. Then I got the grant, and I started doing simulations. This was coming out. Not only does the proportion, you can get the proportion, you get the right number, if it were true. I showed this to my buddy Zidane Bai when he came here to visit, I guess in '92. I showed him the simulations, and we shook hands on working on this. And it took a while. It took the first on what we call exact separation of the eigenvalues. Oh, I throw this in. This is 2 specific cases where we have explicit expressions for limiting density. The case where the Tn is the identity matrix, you have this. It works out to be this density. Okay, this is called these days the Marchenko-Pasteur density. They were the original ones in their paper to have this. And the limits. So it's one hump. You just have one population eigenvalue. It's like noise. The value 1. So and here's another case here where you have a multivariate F matrix. That's the case where your population matrix is random also and is the inverse of another matrix like what you get up here. Just another matrix full of IID variables. And this other case, I have it on the next slide, you have 2 parameters. They have the initial little n to big N, but in this case here, how are you computing this? This is little n to a big N prime. And so the little n to big N prime goes to a number C prime, which has to be less than 1 if you expect to have an inverse out of this. This is the extension of what we call an F variable. A multivariate F matrix, like the extension of a chi-square of a chi-square. And the limiting distribution, this is something I worked out back in 85, turns out to be this thing. Again, it's one hump, turns out. And you get the boundary points. So now, as far as the results on exact separation, I mean, I can skip this. I mean, this is all right. Well, I guess we're not going to get kissed out. Something was resolved.
I think so. Okay.
All right. So now, as far as having, we did it in two parts, and there was the first paper back in '98, where what we need is some consistency as you let the dimensions blow up. So here, let for any positive number d in any distribution function, any probability distribution function g, let it denote the limiting spectral distribution of this matrix, corresponding to limiting ratio d and limiting, which I called earlier, hg. That is, you have the equation, which gives you the inverse of the limiting Stiltz transform. So let's call it D, and let's call it G. So T, dg of T over T plus 1m. So for any positive number D, any probability distribution function G, we have this equation. This will define the inverse of a Stiltz transform. And that's what I'm talking about. So f of dg is the distribution defined by this equation. And the result is that, so we have now, in this case here, we need the entries, the matrix to come from one doubly infinite array of independent identically distributed random variables. With mean 0. Here we assume that the mean has to be 0, the variances are all 1, and the fourth moment's finite. Fourth moment finite is important. Here you make up the matrix. This little xn is going to be the matrix you get from the first little n rows, the first big n columns of this doubly infinite array of random variables. Here we assume from the beginning that Tn is non-random. Once you have this result, you can then assume it's random. It's independent. So, and that the spectral norm is bounded in n. The other case, we didn't have to assume that the spectral norm was bounded, just that the limiting distribution was a proper probability distribution. So you have one or two mass points escaping to infinity. And so we're looking at an interval, which we know that this thing lies in an open interval outside the support of this thing. So this is defined up here for all large n, which should make sense. You don't want to cheat and have it, inside and outside. So we know that this interval is always outside the support for all n large. And the first result is the probability, the event that no eigenvalue of Bn appears in the interval AB for all n large. This event has probability 1. So this will give us the result that no eigenvalues are appearing in places where they shouldn't. Okay. The next result deals in the proper number appearing in the support, or in other words, to the left or to the right of a region that's outside the support. The same number is appearing. Well, it turns out there are two separate cases, which is interesting. In that first case, it turns out it is just plotting the function, that that inverse function is going to do this for positive n. This is the number x0 that I'm talking about. In that first instance, when this thing is bigger than 1, this will imply that c has to be bigger than 1. That means the limiting, you're going to have less samples than vector dimension. Then x0, the smallest value in the support of this, that value x0 there, it will work out. It's all calculus. That and with probability 1, the capital n's, because you're only going to have capital N non-zero eigenvalues. The capital N's largest eigenvalue. So somewhere I should say that as we were ordering these from largest to smallest, the capital N's largest eigenvalue Bn is going to that x0. And that number x0 is the maximum value of this function, of that function. I'm including the rest. Well, in the case where that's less than or equal to 1, or we're in this case, but AB is not contained in that interval 0, x0, then the value, the Stilton's transform are valued at, this is like M underlined, because it's the Stilton's transform involved with the limiting distribution of F underlined. This is the solution of the equation, the Stilton's transform, the distribution you get from the X star T X1 matrix. And it turns out that this is negative, and here's where we do the comparisons. For n large, we'll have an integer in such that the nth largest eigenvalue of Tn is bigger than or equal to this guy, and the in plus 1 largest eigenvalue, this thing is less than or equal to this value here. I'll draw something on the board in 1 second. Oh, here it's non-increasing order. Arranged in non, right? So biggest to largest. And then we have the probability that the inth eigenvalue Bn is bigger than A, B, inth plus 1 first eigenvalue is less than A, or n large is equal to 1. This is as far as where those values come in. So we have the interval AB outside the support, and this will come from one swing of that inverse function. We have values here. Okay. Then we have some vertical asymptotes, and this will correspond to minus 1 over the eigenvalue of Tn, the inth one. This vertical asymptote will occur. Remember, we're plotting x versus m, that inverse function. This is minus 1 over lambda, in plus 1 Tn. These are those 2 points. And these are the 2 values of in and in plus 1. That's the most natural separation. And they occur. And that's so we get the 2 results. So that's been known for a while, and this came out in '99. I always thought that going back, let me go back to the picture, that even though we have things behaving well, and it will help, like, knowing how many enemy things are out there. This is what we call the detection problem. I never thought that one could estimate 10 from this. I always thought it was ill-posed. Is the right term? That you couldn't do it. And I was proven wrong. And this is what I want to go through now. This is, and I will end with an application. But the engineers are very much, estimation scheme is still
because
going
this
on.
is on record, I will say it. So it was only ill-posed until it was well-posed.
I guess so.
Or solved.
Or just, well, here, and now I want to go through the mathematics with you, because this is what I finally met him. We hung out together in Paris. We were both on the advisement. Remember Romain Coulier? He visited with me 3 weeks. But it was Xavier Mestre from Barcelona. He did it. Let me go through the math. So what I want to do first, with that inverse function, you can express it in terms of the Stilton's transform of h of n. This is for a fixed little n, and hn is the distribution function, the eigenvalues of Tn. So we're fixing n. Look in the finite case. And so we can write it this way, just simple algebra. Something else, suppose that Tn has a positive eigenvalue T1 with multiplicity N1. We can get that if there's separation from a realization. We can get what N1 is if we knew, we'd look in one hump there. Like eigenvalue 3, we counted 80, so we would know its multiplicity. Then on any contour positively oriented, encircling only T1 of Tn, this we do, we use Fubini's theorem. Let me go quick with this. The idea is that this thing is equal to T1. T1 we can write in terms of this complex integral, where we integrate over the complex plane, only including eigenvalue T1. Hey, I just save a little time. So we have this expression. Then we do a change of variables. Minus m bar is minus 1 over y. we find that T1 can be written this way. Okay. Where now we throw in, we have the Stiltz transform of H, of M, and write it in terms of that function Z of M. Okay, so again, I'll write it again. Z of M minus 1 over M plus C, T of Hn of T, which is discrete in our case. And so we can write T1 as an integral involving our function here. In the contour with that change of variables is contained the negative real portion of C encircling only minus 1 over T1 and no other eigenvalue of Tn. Okay, now suppose we have exact separation, okay, for the eigenvalues for all n associated with T1. Then the contour can be chosen so it intersects the real line at two places for which this function here is outside the support of this thing, and this interval contains only the support. So see, XA, XB only contains the support. Then with substitution m equals m of z, we have this theoretical result, that T1 can be written as, in terms of the integral of the derivative of that limiting Stiltz transform, it's the m underlined, with the Stiltz transform, the ratio, just by a simple change of variables. And the contour will only contain the support associated with T1. Okay, so this is all just a theoretical result. The idea is that from a sample, from a realization, we can estimate m and its derivative very, very well, just by the eigenvalues. They're just, defined, the m will just be the sample eigenvalues. And in fact, results that I've been involved with, we know that the estimation is pretty good of the Stiltz transform. And away from the support of the distribution, but we are away from the support. These are going to be outside the support. It's going to hit the real line places outside the support. So we're going to use the result that so this is now, so m underline n is your random Stiltz transform. Stiltz transform of the eigenvalue involved with the eigenvalues of this matrix. And what we do know is that these go together very quickly. In fact, they go together like 1 over n, 1 over the dimension, as the dimension blows up. So replace m underlined by mn, the sample, and derivative here. And we have an estimate. This is taken as an estimate of T1. The quantity, you work it out with all residue theory. Where does this blow up? This blows up wherever this becomes 0, and we're at the eigenvalues. Okay, so wherever we're at the eigenvalues, this blows up, and wherever this is 0. And it turns out to be exactly this. This estimate is equal to, in terms of your random eigenvalues, the eigenvalues are inside that interval, corresponding to the population eigenvalue, but also the zeros of the Stiltz transform. So and they're the same number. You can show that the same number because the zeros of Stiltz transform, places where the Stiltz transform goes from minus infinity to infinity, and it increases and hits 0 only one spot at each place in between the eigenvalues. And one fact, this is something you write the Stiltz transform of the eigenvalues of x star tx, and this is equal to 0. You can work it out that you got the little n eigenvalues. The eigenvalues of Bn will satisfy this equation. Anything that's 0, just from algebra, you get this. And anybody that's worked with updates of rank 1 matrices, I remember, as soon as I saw that, I realized, hey, those are the eigenvalues of a matrix where you're updating something. Without going into any details, it's actually, the solution of those are actually the eigenvalues of this matrix. So the diagonal matrix consisting of the eigenvalues minus 1 over capital N times the outer product of the square roots of these things. I can discuss this afterward, but this really comes directly from whatever you write, whatever you want to find the eigenvalues of a rank 1 update of one matrix. It's always, if you want to see the coefficients here, this is where you get the square roots, and this is where you get the earlier eigenvalues. All right, so you can get those zeros just from another eigenvalue routine. When this is that student Vermont Coulier, he was showing me this. I said, I don't believe it. I went back to the simulation I did back in the mid-90s. I still have the data, and I punched in those values, and this was the comparison I got from that simulation I showed you. So eigenvalue 1, this value. Eigenvalue 3. This guy did it. He really did it. And I was amazed. And it's mainly, it's also, the big factor is that people are working on showing that the actual deviation is going Gaussian. And when you multiply just by the dimension. Okay, let me finish up with an application to wireless communications with Roman, his student, his advisor, my buddy Bai. Something that's in our book, actually Springer published it in 09, but December 01. But some places has it 10. So anyway, so if you replace the assumption in my original paper where that's okay, but I'm going beyond identically distributed. They're independent, common mean, unit variance, don't have to be mean zero, such that for any eta, this is a statement on the tails, the common tail. This is kind of like the Lyapunov condition involving the tails of your distribution. And if this is true for every little n and big N, that this thing goes to zero, then the conclusion of what I had in the first theorem, that the limiting eigenvalues are convergent. So this goes beyond independent, identically distributed to arbitrary distributions. Still variance 1, expected value of the square of the matrix, the square of the random entry minus its own expected value is 1. Then the results are true. And also in the paper that we're going to give the final result, if we wanted to extend the exact separation distance. So replace the first assumption in the paper with Bai is that they are independent, mean 0, also variance 1. We needed mean 0 to get the exact separation. And that there's a constant, something that will take the place of finite fourth moment. Well, if this is true, if we can find a random variable or a distribution, if you want, for which this averaging of the tails is always bounded by some fixed constant times the probability that this random variable is bigger than x in absolute value. Okay, that's the second assumption. And there was another one involving the existence of a function that blows up and a positive n for which these guys, the max of all these things, is bounded. Then the conclusions of what Bai and I had done on exact separation are true. We're using that for a result in power estimation of lots of signals. Think of cell phones in an environment. You have k entities transmitting data. There's capital K. Each one has an unknown transmission power with little n antennas. They transmit data to capital N sensing devices. So think of one tower with capital N antennas. The multiple antenna channel matrix between transmitter K and...
It's all right.
Next time use the bad hands.
It's all good. Okay. I'll need
Actually, it's easier to see.
Between transmitter little k and the receiver is denoted by, this is what they call a fading channel. So you're going from the antennas in the one device to the group of capital N. So this is, so you're doing matrix vector multiplication for the antennas. And they're assuming, in fact, engineers have told me, this is known in the 80s, these fading channels are very well approximated by entries that are complex Gaussian. This is what comes in when a signal goes and bounces off walls and does everything else, splits up. The central limit theorem takes over. And so, the scaling here is this for our result. At any instant of time, transmitter K emits a signal where it is assumed that they are independent and standardized independent for different M's. So this is sampling signals from all the capital K antennas, all the capital K users. Each of them has little ends of K antennas. And at the same time, the signal is impaired by added noise. Okay, I guess the signal coming on to the receiving end. Okay, so there's ambient noise coming in, and they're assumed IID standardized. So this is where we needed different assumptions on the distribution. Because basically, from what I understand, what's coming from the individual cell phones, whatever, can be modeled very well by independent, identically distributed, but discrete random variables. They're like digital things. They're coded. And so therefore, at time little n, the receiver senses this signal, comes in. You do a linear transformation for each of the K entities, hidden off this, and here is the unknown power. That's just a scalar. The P's are unknown, and everything else is random. H is still not known. You just know it's the distribution. So something random here. This is random. We can put everything in terms of in block form. So if capital Y is just the columns of those coming in. So capital Y is big N by big M. And X contains for each different person or user. And W involves the noise. You can write all this in terms of one big matrix. Okay. And the idea is, so this contains, well, we're looking at this matrix, and we want something to do with the eigenvalues of something. We're basically going to look at the eigenvalues of Y times its transpose. Little n is the sum of all the different transmit antennas, and big X is a big column form. This one, big X is this. P is diagonal, containing all the, right? It's the right thing to have it in the total block form. H will be this. So you see, the X is hitting the powers, and all this is hitting the H's, and that's for each column. And then the P matrix contains all the individual powers. P1 so many places, n sub 1, P2, n sub 2, and so on. And it's really the square root of the powers. And the goal is to estimate the P's. We estimate these powers. Notice, well, we can put Y as the first big N rows of this matrix. Notice it's this, X times this, and the noise part with the W. And just let's tag on some zeros, so this is a square matrix. This we can consider, or this times its transpose, we consider as a population matrix. But this is random also. This is where we need the fact that the results of exact separation are also true for when your population matrix is random in itself, which can be achieved without any difficulty in math arguments. Okay, and we have the previous results, and the main result is that, well, the first is telling us, so we're looking at this matrix here, which is big N by big N. Almost surely this thing converges in distribution to it's something where it's Stiltz transform is equal to this, and this Stiltz transform here. This is it's a unique solution, but it is a Stiltz transform. It's a unique solution with positive imaginary part to this. So here we're assuming capital K is fixed and everything else blows up. It's here. So the number of transmit antennas is proportional to the number of the received antennas. So they're all blowing up and going to a positive constant. And you basically solve, it's the...
Do you assume any kind of separation on the powers?
Yes, we're assuming that here we don't assume separate. They can be the same for this result. For the next one, though, we have to assume that they're separate, that they're going to be the same. Oh, I see. All right. So MF, this guy here, is equal to this, but F is equal to this. So MF solves an equation involving MF itself. So F is actually, to try and simplify the expression. And we get it from the results that as far as the original paper that I presented. As far as estimating the powers, it turns out here we need them to be separate. Okay? And the other assumptions which are needed is that there are more samples than the number of receive antennas, and the total number of transmit antennas, that's what little n is less than the number of the receive antennas. And certain assumptions, other assumptions that's in the paper, and so that which will allow exact separation. That you're going to get things involving the p's separated. The eigenvalues associated with the different p's will be separated from each other. And to note the smallest eigenvalue. So S is this, and it turns out that this figure here, this quantity here, where the etas and the mu's are given by this. Notice it's going to involve eigenvalues. It's going to be zeros involved with certain Stiltz transform. The difference between the two is big N and big M here. So it's actually the zeros that came out to be the relevant thing. And this is the right number in here as far as how they're arranged. But these are the right estimates for our powers. In the paper, it appeared already in IEEE information for 2011. And using similar ideas. So this stuff is still going on with estimating the population eigenvalues. Engineers are attacking it, and so we put our toes in it. These are people. Merwan Damar is head of a group at Supelec, south of Paris, and Romain was his student. And they wrote a nice book, Random Matrices for Wireless Communication. That's it. That's all I want to say. Thank you.
More questions, comments?
So in my neighborhood, every one of my channels is fading. And it keeps fading out over and over.
I don't know where that term comes from. They use that term. You transmit from a vector of antennas to another vector without any outside noise. And it's this fading channel which is generated because of the buildings and the interference, but then it's fixed. Nothing else changes. And it's been modeled very well since the late 40s, from what I understand. Really? I think really?
So this n goes to infinity.
The bigger, yes. This is all results for in the limit what's happening, but we take it for with simulations. It's working out very nicely. So all these results are are limit theorems, but it's like.
So do you try to go back from infinity?
Oh, we're going.
And,
we're not.
and try to say, well, if n is greater equal to 200, then
That's a tough
this
thing.
expression has that error term at most that error.
Other
term.
people are trying to do that. That's where you come in with central limit theorem. If they try to get how far the difference between the p hat and p, subtract away, multiply by the right scaling factor. If you show it goes here, then that gives you an error estimate. In fact, it has been worked out by colleagues of mine in Paris working on.
You just want that the error would be less than a certain amount with a certain probability, right?
Yeah, that's always the case. I mean, if you show that it goes Gaussian, then you can use a Gaussian table to predict. But my advice is use it. You get it, and especially the exact separation business. I mean, it's pretty dramatic. I've never seen it crossing over in the middle.
You don't use it, you lose it.
Anything else? Anything else? Okay, great. Thank you.